Welcome to the last signal. Before there were stars, before there were galaxies, before there was a single planet turning in the dark, the universe was already becoming something. Not something calm, not something familiar. Something so young that even the words we use for reality begin to feel too small. There is no night sky yet, no constellations, no worlds. No silence between stars, because the stars themselves had not been born. And yet, inside that early darkness, the future was already being prepared. The matter in your body, the light in every telescope image, the shape of galaxies, and the empty-looking space between them all trace back to a time when the universe was still learning how to become readable. This is a story about the first thresholds. The moments when rules separated, matter survived, light was trapped, darkness took shape, and the visible universe slowly gained the conditions it needed to exist. And if you are watching on YouTube, leaving a like helps this kind of quiet documentary work reach more people. Now we begin near the first boundary of time, where physics still touches the edge of what it can explain. The first moment of the universe is not best understood as an explosion in the ordinary sense. An explosion happens somewhere, inside space, with material flying outward into an already existing emptiness. But the beginning of the universe was stranger than that. It was not matter expanding into a room. It was the room itself, the distances themselves, the possibility of separation itself, entering a state of expansion. At the edge of that beginning, familiar words start to fail. Temperature, density, energy, time, and space still matter, but they no longer behave like the quiet, reliable ideas we use in everyday life. There is no sky to look at, no center to point toward, no outside darkness waiting around the edges. There is only a condition so compressed and so extreme that the tools of ordinary imagination have almost nothing to hold on to. When cosmologists try to understand the early universe, they do something both simple and dangerous. They take the expansion we observe today and run it backward. Galaxies come closer together. The space between them shrinks. The universe becomes hotter, denser, and more energetic. If that backward path is followed far enough, it leads toward a boundary where the observable universe was squeezed into scales so small that our best theories begin to strain. This does not mean science has nothing to say. It means science reaches a wall where two extremely successful descriptions of reality must be used at the same time, even though they do not yet fully fit together. On large scales, gravity is described by general relativity. That theory tells us how mass, energy, space, and time shape one another. It explains the motion of planets, the bending of light near massive objects, the expansion of the universe, and the deep structure of black holes. On the smallest scales, reality is described by quantum mechanics. That theory deals with particles, probabilities, fields, and the strange rules that govern matter and energy when everything is reduced to its smallest known behavior. Both theories are among the most powerful achievements in the history of physics. Each has been tested with extraordinary precision. Each works beautifully in the world it was built to describe. But the earliest universe demands both at once. It asks gravity to behave quantum mechanically. It asks space and time themselves to enter the restless, uncertain world usually reserved for particles and fields. And that is where the difficulty begins. A useful way to picture the problem is to imagine two maps. One map is drawn for continents, oceans, mountains, and cities. The other is drawn for the inside of a machine, where every screw and wire matters. Each map may be perfect on its own. But if someone asks you to place both maps on the same sheet of paper, with every detail matching, the lines no longer agree. The early universe forces physics into that impossible overlap. The enormous and the tiny are no longer separate realms. Gravity is not a distant background effect. Quantum uncertainty is not a small correction. They are both part of the same event. This is why physicists speak of the Planck era with such caution. The Planck era refers to the earliest boundary we can meaningfully discuss using the deepest measuring ideas in physics. Planck time, Planck length, and Planck temperature are not ordinary measurements in the way seconds, meters, and degrees are ordinary measurements. They are signs that we have reached scales where the usual language of time, distance, and heat is close to breaking. A second is already far too large a container. A meter is far too wide. Even the idea of a single location becomes difficult, because space itself is part of what is being questioned. Pause there for a moment. Imagine trying to measure a storm with a ruler that melts when it gets near the clouds. Imagine trying to weigh a flame on a scale made of smoke. That is not because the storm or the flame is unreal. It is because the measuring tool belongs to a calmer world. The Planck era is like that. It is not a place where scientists simply need a better telescope. It is a regime where the concepts behind the telescope, the ruler, and the clock may need to be rebuilt. This is the first locked door in the story of the universe. Behind it may be a deeper theory of quantum gravity, a theory that joins the smooth curvature of general relativity with the restless grain of quantum mechanics. Physicists have proposed possible paths toward that theory. Some imagine space and time as emerging from something more basic. Some try to quantize gravity itself. Some suggest that the beginning may not be a simple beginning at all, at least not in the way human language naturally pictures one. But none of these ideas has yet become a confirmed final account of the first instant. That distinction matters. The early universe is not a gap that can be filled with confident storytelling. It is a frontier where the evidence becomes indirect and the mathematics becomes difficult to test. So the honest picture is more powerful than a simple one. The universe is about 13.8 billion years old, and we can trace much of its history with remarkable success. We can describe the cooling of matter, the birth of the first nuclei, the release of ancient light, and the slow growth of cosmic structure. But at the very beginning, before physics had settled into the shape we recognize, knowledge meets its first horizon. Reality has begun. Expansion has begun. Something like time is already part of the story, but the rules that will later make the universe readable are still hidden inside the heat. Long after the first boundary of time, the universe we know is held together by four fundamental forces. They are so familiar in their effects that we usually do not notice them. Gravity keeps your feet on the floor and holds planets in orbit around stars. Electromagnetism lets light reach your eyes, gives matter its structure, and allows atoms to form bonds. The strong nuclear force locks the cores of atoms together, binding quarks inside protons and neutrons, and holding atomic nuclei in place. The weak nuclear force works more quietly, shaping certain kinds of particle change and making some forms of radioactive decay possible. These forces are not distant cosmic decorations. They are present in the weight of a stone, the warmth of sunlight, the chemistry of the blood, and the silent stability of every atom in the body. A human hand lifting a cup, a star burning in space, and a galaxy bending the path of light all belong to the same physical order. That is the first strange thing. The rules that govern the largest structures in the sky also reach into the smallest parts of ordinary matter. But in the earliest universe, even those rules may not yet have looked separate. The young cosmos was not simply hot in the way a fire is hot. It was filled with energy so high that differences, which seem absolute today, could blur into a more unified state. At lower energies, forces appear distinct. They have different strengths, different ranges, and different ways of acting on particles. But at extreme energies, physicists expect that some of those divisions can disappear. The clearest example is the electroweak force. In modern particle physics, electromagnetism and the weak nuclear force are understood as two faces of a deeper electroweak interaction at very high energies. As the universe cooled, that shared behavior separated into the electromagnetic force and the weak force we observe today. This is not merely a poetic idea. It is part of tested particle physics, supported by the structure of the Standard Model and by experiments carried out in powerful accelerators. Grand unification is a more ambitious step. It suggests that the strong nuclear force might also join the electroweak interaction at energies far beyond what we can easily reproduce. That idea is elegant, and it has guided generations of theoretical work. But it has not been confirmed in the same way as electroweak unification. It remains a possible deeper pattern, not a completed piece of established history. Gravity is more difficult still. It shapes the expansion of the universe, the fall of matter, the motion of galaxies, and the curvature of space-time. Yet it remains the force that resists being placed neatly inside the same quantum framework as the others. The early universe therefore sits in a strange position. It appears to be moving from unity toward difference, from an almost hidden simplicity toward the recognizable forces that will later build matter, stars, and galaxies. A helpful image is cooling metal. When metal is white hot, its details are swallowed by brightness. Edges, color, and surface all seem to disappear into one fierce glow. As it cools, shape returns. The boundary becomes visible. The object begins to reveal what it is. The early universe changed in a similar way, not because it became calm, but because falling energy allowed distinctions to appear. Each drop in temperature was not just a quieter state. It was a new permission. It allowed one kind of behavior to split from another. It allowed one interaction to take on its own identity. It turned a universe of blurred possibilities into a universe with rules that could begin to act separately. This is why cooling is not passive in the story of the cosmos. Cooling is a form of creation. It does not add material from outside. It changes what the material can do. A newborn universe can be thought of as a locked room slowly receiving keys, but those keys are not objects. They are rules. Gravity begins to take its role. The strong force prepares the way for the binding of matter. The weak force opens paths for particle change. Electromagnetism waits to shape light, atoms, chemistry, and eventually every visible surface in the universe. There is something almost unsettling about this. The same interactions that will one day allow a leaf to catch sunlight, a nerve signal to move through a body, and a compass needle to turn were already being defined in the first fractions of cosmic history. The ordinary world was not present yet. There were no atoms, no stars, no planets, and no eyes to see anything. But the permissions for those later things were beginning to separate. The universe was becoming less like a featureless blaze and more like a system with parts that could behave differently. It was still violent. It was still dense. It was still almost impossible to picture. But it was no longer completely without shape. The first forces had begun to step out of the heat. The young universe presents a contradiction before it offers an answer. When we look across the observable cosmos today, we find that distant regions have almost the same background temperature. They are not perfectly identical, but they are far more alike than simple expansion would make easy to explain. This becomes strange when distance is taken seriously. Light has a speed limit. Information has a speed limit. Heat cannot travel from one side of the universe to the other if the two regions have never had enough time to communicate. Yet the ancient glow that reaches us from opposite directions looks as though those distant regions once shared a common condition. This is called the horizon problem. It is not a small technical inconvenience. It is a sign that the visible universe appears too coordinated for the time available. If two rooms have never been connected and no messenger has ever passed between them, we would not expect them to settle to nearly the same temperature. But the universe seems to have done something like that. A second difficulty appears in the shape of space itself. On the largest observable scales, the universe appears extraordinarily close to flat. Flat does not mean thin like paper. It means that cosmic geometry, when measured across vast distances, behaves very close to the balanced middle case between curving back on itself and opening too strongly. The strange part is how precise that balance must have been in the early universe. A tiny departure from flatness should have grown with time. If the initial value had been even slightly different, the universe we observe today would look radically unlike the one above us. This is the flatness problem. A third clue came from certain high-energy theories. Some versions of grand unification suggested that magnetic monopoles should have been produced in the early universe. A magnetic monopole would be like a magnet with only one pole, north without south, or south without north. Ordinary magnets do not behave this way. If such objects were created in abundance, we might expect to see evidence of them, but they have not appeared in ordinary observations. Taken together, these problems made the early Big Bang picture feel incomplete. The universe was too even. It was too geometrically balanced, and some predicted relics seemed to be missing. Cosmic inflation was proposed as a way to make these puzzles belong to the same deeper event. Around the end of the 1970s, physicist Alan Guth developed an early model of inflation. The idea was startling in its simplicity. For an extremely brief interval, the universe may have expanded at an overwhelming rate. Not quickly in the ordinary sense of an object moving through space. Space itself expanded. A tiny region could be stretched until it became large enough to contain everything we now call the observable universe. This changes the horizon problem. If the visible cosmos began as a much smaller region, its distant parts could once have been close enough to share a common state. Then inflation pulled those parts away from each other faster than gradual expansion alone would have done. The similarity we observe today would not need to be created across impossible distances. It would be inherited from a time when those regions were once neighbors. Inflation also helps with flatness. When a surface is stretched far enough, local curvature becomes harder to notice. A small wrinkle can be enlarged until the piece we stand on appears nearly smooth. The universe may have gone through something similar. A region with curvature could be stretched so enormously that the part visible to us appears balanced and almost flat. The missing monopoles become easier to understand as well. If any were produced before inflation, the expansion could have diluted them so severely that they became extraordinarily rare within the observable region. They would not need to be absent from all reality. They could simply be spread so thinly that we are unlikely to encounter them. This is why inflation became so powerful. It does not answer one puzzle in isolation. It links several strange facts to one rapid transformation. But it should not be treated as a finished photograph of the first moments. Inflation is widely used because it explains important features of the universe with remarkable elegance. Its exact mechanism, however, remains an active subject of research. Physicists still investigate what field or condition drove it, how it began, how it ended, and whether it happened in the precise form our models suggest. The idea is influential, but it is not a closed door with every lock solved. There is another consequence, more delicate and perhaps even more important. Before inflation, quantum fluctuations would have existed as tiny irregularities. In the quantum world, fields are never perfectly still. They tremble with minute variations. Inflation could take those nearly invisible differences and stretch them across cosmic distances. A whisper in the smallest fabric of reality could become an echo large enough for gravity to hear. A tiny crease could be magnified until it crossed a continent of space. These stretched irregularities would later become differences in density. Some regions would be slightly richer in matter. Others would be slightly thinner. For a long time, the difference would be almost imperceptible. But gravity is patient. It works with small advantages. It gathers where there is already a little more to gather. In this way, inflation does more than make the universe larger. It may preserve the first uneven marks from which later structure grows. Galaxy clusters, galaxies, stars, and eventually planets may trace their ancestry back to those small early variations. That thought changes the scale of the story. The universe we can observe may not be the whole universe. It may be only one expanded patch, one region that light has had time to reveal to us. Beyond that horizon, space could continue far beyond what any telescope can show. Inflation does not require us to claim certainty about everything outside view. It simply reminds us that the visible cosmos may be local, not total. The first great stretch may have made our universe look smooth, flat, and empty of certain relics. But at the same time, it preserved tiny imperfections. And in those imperfections, structure was quietly waiting. One of the simplest questions about the universe is also one of the deepest. Why does anything resist motion? Why does a stone feel heavy in the hand? Why do particles not all rush through space like light? It is easy to treat mass as if it were just a basic fact, something matter naturally has because matter exists. But in modern physics, that answer is not enough. Mass is not simply a label placed on particles after the universe has already formed. It is part of a deeper physical story about fields, broken symmetry, and the way empty space is not truly empty. In the earliest universe, before familiar matter had settled into stable forms, many particles behaved differently from the way they behave today. The newborn cosmos was still cooling. Its rules were still taking on their separate identities. And one of the most important changes involved the question of which particles could gain rest mass. To understand why that matters, symmetry has to be described in ordinary language. Symmetry means that something can change in a certain way while still remaining, in some deeper sense, the same. A perfect circle looks the same after it is rotated. A smooth lake can reflect the sky without choosing one direction over another. In physics, symmetry is more abstract, but the basic feeling is similar. It is a kind of balanced sameness. At extremely high energies, some parts of reality may hold that balance. As the universe cools, the balance can break. This does not mean that something has gone wrong. It means that a hidden possibility has chosen a particular form. The same laws remain underneath, but the world no longer looks the same in every direction of possibility. This is where the Higgs field enters the story. The Higgs field is not a substance floating through space like dust. It is not an invisible liquid filling the universe. It is a physical field, present throughout space, whose presence changes the behavior of certain fundamental particles. Some particles interact strongly with this background condition. Some interact more weakly. Some do not interact with it in the same mass-giving way at all. That difference helps explain why many particles have mass, while others remain massless. Photons, the particles of light, remain massless in the Standard Model. Gluons, which help bind quarks through the strong nuclear force, are also massless. But the W and Z bosons, connected to the weak nuclear force, are massive. That difference is not a minor detail. It shapes the range and behavior of the weak force itself. It helps explain why one interaction acts over tiny distances, while light can cross the universe. The Higgs field is therefore not an ornament added to particle physics. It is part of the reason the world has the structure it does. Pause for a moment on what that means. Space is often imagined as absence. An empty room, a blank stage without furniture, a silent gap between objects. But the deeper picture is stranger. Even when space contains no dust, no gas, no stars, and no visible matter, it can still have physical properties. It can contain fields. It can set conditions. It can determine how particles move, how they interact, and whether they carry rest mass. Empty space is not nothing. It is more like deep water that looks still from above, while currents below the surface decide how everything drifting through it will move. This comparison is imperfect, because the Higgs field is not made of water, and particles are not little boats, but it gives the right sense of hidden influence. The most important features of reality are not always visible as objects. Sometimes they are conditions that everything else must pass through. The detectable sign of the Higgs field is the Higgs boson. A boson can be thought of as a quantum ripple of a field. For decades, physicists searched for this particular ripple. The search required enormous machines, extraordinary precision, and collisions energetic enough to briefly reveal what ordinary conditions keep hidden. In 2012, scientists at the European Particle Physics Laboratory, CERN, announced the discovery of a particle consistent with the Higgs boson. That announcement did not answer every question about mass. It did confirm a central piece of the Standard Model. It showed that the hidden mass-giving layer in modern particle physics was not just mathematical decoration. It had left a detectable trace. Still, care is needed here. The Higgs field explains why many fundamental particles have mass, but most of the mass in ordinary matter does not come directly from the Higgs field in a simple one-to-one way. Protons and neutrons are made of quarks, and the majority of their familiar mass comes from the energy of quarks and gluons bound together by the strong nuclear force. That is why mass is not a single simple thing. At one level, particles gain mass through their relationship with the Higgs field. At another level, the matter inside atoms gets most of its weight from the intense energy held within protons and neutrons. The early universe needed both parts of that story. It needed fundamental particles to stop behaving as if everything were weightless light. It needed interactions that could create differences between one particle and another. And later, it would need bound systems whose internal energy could become the mass of ordinary matter. In the young cosmos, this changed the future. Once particles had mass, they no longer all moved in the same way. They could slow relative to light. They could respond differently to forces. They could become ingredients in a universe where gravity would eventually have something to gather. This did not create atoms yet. It did not create stars. It did not even create stable protons and neutrons in the ordinary sense, but it gave the particle world distinct identities. The universe was no longer only a field of extreme energy and blurred possibilities. It had begun to sort its contents. Some particles remained messengers of massless motion. Others became heavy enough to change how forces behaved. And through that shift, the young universe took one more step away from pure heat and one step closer to matter. There was a time when the universe contained particles, but not yet atoms. There was energy, motion, pressure, heat, and interaction, but not the stable architecture that later makes ordinary matter recognizable. No carbon, no oxygen, no iron, not even hydrogen atoms in the familiar sense. The young cosmos had not yet built the quiet pieces from which chemistry could begin. It was still too hot for that, too crowded, too restless. At this stage, the universe was filled with a quark-gluon plasma. That phrase can sound distant, but the idea behind it is direct. Quarks are among the fundamental ingredients of protons and neutrons. Gluons are connected to the strong nuclear force, the interaction that binds quarks together. In the world we know, quarks are not found drifting freely through ordinary space. They are confined inside larger particles. But in the early universe, the temperature and density were so high that matter existed in a more exposed and unsettled condition. The pieces were present, but they had not yet locked into the shapes we would recognize. Think of wet clay before it holds an edge. It has substance. It can be pressed, moved, and reshaped. But it has not hardened into a brick, a bowl, or a wall. The quark-gluon plasma was not clay, of course. It was a blazing state of fundamental particles and force carriers. But the comparison helps capture the feeling of matter, almost becoming itself. The ingredients were there. The form was not. As the universe expanded, it cooled. And as it cooled, the strong nuclear force began to act in a way that made free quarks impossible to keep apart. This process is called confinement. Quarks became bound into hadrons, a larger family of particles that includes protons and neutrons. A proton contains 2 up quarks and 1 down quark. A neutron contains 2 down quarks and 1 up quark. Those combinations may sound almost too small to matter, but they are among the first stable patterns from which the later universe will be built. A proton is not just another particle in this story. It is the nucleus of a hydrogen atom, and hydrogen will become the most common ordinary element in the cosmos. Neutrons are just as important, although their role is different. They help make heavier nuclei possible. Without neutrons, the early universe could not move beyond isolated protons in the same way. The difference between a proton and a neutron is small, but it is not meaningless. A neutron is slightly heavier than a proton. That small mass difference helped shape how many of each survived as the universe cooled. Over time, some neutrons decayed. Protons became more numerous. The balance between them would later determine how much hydrogen and helium could form. Here again, a tiny difference becomes a cosmic decision. The early universe was not yet making planets, oceans, or living bodies. It was deciding the inventory from which all later visible matter would draw. Pause inside that thought for a moment. There is still no solid surface anywhere. No dust grain floating in starlight. No star to create that light. No atom with electrons circling a nucleus in the ordinary picture people learn at school. There is only a dense, hot, expanding environment where the first durable pieces of nuclear matter are beginning to appear. It is like watching loose stones settle into the first layer of a wall, long before anyone can see the building. The wall is not there yet. The rooms are not there. The roof has not been imagined. But without that first layer, nothing later can stand. The strong nuclear force is the hidden grip that makes this possible. It does not behave like gravity, reaching across astronomical distances. It does not behave like electromagnetism, shaping light and chemistry across the visible world. It acts over extremely short distances, but inside those distances, it is powerful enough to bind quarks into stable combinations. That binding is one reason matter can hold together at all. It gives protons and neutrons their internal structure. It prepares the raw material for atomic nuclei. It turns a universe of loose fundamental ingredients into a universe with the first rough stones of matter. This stage also marks a change in the way the cosmic story feels. The earliest moments were dominated by hidden laws, separated forces, and fields taking form. Now something more concrete is beginning. Not atoms, not elements in the chemical sense, but the cores of future atoms are becoming possible. Protons and neutrons are still surrounded by heat, radiation, and constant interaction. The universe remains far from calm. Any fragile structure would be challenged by the energy around it. Yet a threshold has been crossed. Matter is no longer only a restless collection of smaller pieces. It has begun to hold shape. And once matter can hold shape, the future becomes different. Gravity will later gather it. Nuclear reactions will later transform it. Stars will later ignite from it. Planets will later inherit it. But at this moment, there are only the first durable particles, newly formed from a hotter and more fluid state. The universe now has the rough stones from which atoms will eventually be built. Atoms themselves are still far away. The most ordinary fact about the universe is also one of its deepest unsolved questions. There is matter. There are galaxies, stars, planets, stones, oceans, hands, eyes, and minds. The world did not vanish into pure radiation before it had time to become anything else. That may sound too obvious to need explaining, but in the earliest universe, it is exactly the thing that becomes difficult. Modern physics tells us that matter has an opposite. This opposite is called antimatter. Antimatter is not fantasy, and it is not simply an idea created for equations. It exists. It has been produced and observed in laboratories. It appears in certain natural processes. It behaves in ways that are deeply connected to ordinary matter, but with key properties reversed. An electron, for example, has an antimatter counterpart called the positron. When matter and antimatter meet, they do not usually pass through each other like harmless shadows. They can annihilate. In annihilation, the mass of both particles is converted into energy. The two sides cancel in a way that is almost perfectly balanced. Imagine two waves moving toward each other across still water. If their shapes are matched in just the right way, crest meets trough, motion meets motion, and the surface can flatten. Something was there. Then the pattern disappears. Matter and antimatter are not literally water waves, but the comparison gives the right feeling. When they meet, the result is not one side winning in an ordinary fight. It is mutual disappearance into energy. This creates a problem. In the extreme heat of the early universe, energy could produce particles. But if matter and antimatter were created in nearly equal amounts, they should have found each other again. They should have annihilated. The young cosmos might have been left with radiation, light, and almost no lasting material from which to build stars or planets. There would be no hydrogen clouds waiting for gravity, no first galaxies, no chemistry, no bodies made from ancient particles. The universe would still exist, but it would be almost empty of the kind of matter that makes structure possible. And yet, that is not the universe we inhabit. Somehow, matter gained an advantage, not a large advantage, not a dramatic victory visible as a great cosmic battle. A tiny surplus, a slight imbalance, a difference so small that it almost disappears when spoken aloud, but large enough to become everything later. For every enormous number of matter and antimatter particles that destroyed one another, a small excess of matter seems to have remained. That leftover became the material foundation of the visible universe. This is the matter-antimatter asymmetry. In more technical language, physicists connect this problem to baryogenesis. Baryogenesis refers to processes in the early universe that could have produced more baryonic matter than antimatter. Baryons include particles such as protons and neutrons, the heavy ingredients that later become atomic nuclei. The challenge is not simply naming the process. The challenge is explaining it well enough and proving that the explanation matches the universe we actually observe. Physics does contain real examples of symmetry violation. Some particle processes do not behave exactly the same when matter is exchanged with antimatter. The weak nuclear force plays a role in some of these asymmetries. These discoveries are important because they show that nature is not perfectly balanced in every particle process. The ledger is not always written with identical marks on both sides, but the known violations appear too small, or at least incomplete, when compared with the great matter surplus seen across the observable universe. That is why this question remains open. Something in the early universe may have favored matter by a tiny amount. There may have been processes beyond those we have confirmed. Neutrinos may be connected to the answer in some models. Other theories suggest heavier particles or conditions that existed only at energies far beyond modern experiments. But none of these possibilities can simply be declared the final solution. The existence of matter is evidence that an imbalance occurred. The mechanism behind that imbalance is still being investigated. Pause inside the alternative for a moment. Imagine a universe where every particle finds its opposite. Each meeting leaves energy behind. The temperature falls. The expansion continues. But no durable matter remains in sufficient amounts to gather, cool, and build. No dense clouds. No stars burning in the dark. No planets forming from dust. no later observers wondering why anything exists. Only a fading ocean of radiation, stretched thinner and colder by expanding space. That silent possibility makes the real universe feel less inevitable. The fact that anything remained was not a decorative detail. It was the condition for every later chapter of cosmic history. The first elements depended on it. The first stars depended on it. The galaxies visible through modern telescopes depended on it. Every atom in a human body belongs to the side that survived. This does not mean matter was morally special, or chosen, or destined. It means the laws of the early universe allowed a small imbalance to persist. The difference may have been almost nothing at the beginning, but gravity, time, and expansion are able to work with almost nothing. A small excess can become a cloud can become a star can change the chemical future of space, and much later, that chemical future can become worlds. At this stage, the universe has not yet reached atoms, light, or galaxies. It has only crossed one of the most important thresholds in its entire history. It did not erase itself back into balance. A tiny surplus of matter remained, and that surplus became everything. Every second, particles pass through Earth as if the planet were almost transparent. They pass through stone, metal, ocean, bone, and living tissue. They cross the body without warmth, pressure, sound, or pain. They leave no mark that ordinary senses can detect. These particles are called neutrinos. They are among the quietest messengers in physics. Light can be blocked by a wall. Radio waves can be absorbed. Dust can dim starlight across interstellar space. But neutrinos interact so weakly with ordinary matter that enormous numbers of them can pass through a human body without a single noticeable collision. That is what makes them difficult, and that is what makes them valuable. In the early universe, even neutrinos were not always free. The young cosmos was so dense and energetic that almost everything was forced into constant interaction. Particles collided, scattered, transformed, and exchanged energy in a state where escape was not yet simple. A neutrino may be ghost-like today, but in the first stages of cosmic history, even ghost particles were caught in the crowd. Then the universe expanded. The temperature fell. The density weakened. And at around the 1 second era after the Big Bang, neutrinos are expected to have decoupled. Decoupling means that they stopped interacting often enough to remain tied to the hot particle environment around them. They slipped out of the constant exchange. From that moment, they could stream freely through expanding space. This matters because neutrinos may carry an imprint from a time far earlier than the ancient radiation we can observe most clearly today. Photons, the particles of light, remain trapped for hundreds of thousands of years after this point. They were scattered again and again by charged particles. They could not yet travel across space in a clean path. Neutrinos escaped much earlier. If we could read that ancient neutrino signal directly, it would open a window toward the universe when it was only about 1 second old. That possible signal is called the cosmic neutrino background. It is one of the most haunting predictions of modern cosmology. It should exist. It should surround us. It should pass through everything, everywhere, all the time. But detecting it directly is extraordinarily difficult. The problem is not that neutrinos are absent. The problem is that they almost never announce themselves. To catch even modern high-energy neutrinos, scientists build detectors on enormous scales. Some are placed deep underground. Some use vast volumes of water. Some wait inside Antarctic ice, where a rare interaction can produce a tiny flash of light. The detector is not like a camera pointed at the sky. It is more like a silent lake buried under the world, waiting for one nearly invisible raindrop to disturb its surface. For long stretches, nothing seems to happen. Then, sometimes, a particle that has crossed absurd distances strikes matter in just the right way. A faint signal appears, a brief trace, a small sign that something almost untouchable has passed through. That is already difficult with neutrinos from the sun, from supernovae, or from violent cosmic events. The relic neutrinos from the early universe are even harder. They are expected to be extremely low in energy today, cooled and stretched by the expansion of space across nearly the entire history of the cosmos. They do not arrive like bright sparks from a recent explosion. They would be more like a whisper left from the universe's first breath. And a whisper that passes through walls is not easy to record. This is why the cosmic neutrino background has not been directly detected in the same straightforward way as the cosmic microwave background. Its existence is supported by the structure of the theory and by indirect constraints. It fits into the broader picture of a hot, dense, early universe that expanded and cooled. But the actual act of catching those ancient neutrinos remains beyond ordinary measurement. There is a deep patience built into this kind of science. It does not rely only on seeing bright objects. It also asks what must have escaped before brightness could travel freely. It follows particles that almost refuse to touch the world. It builds instruments large enough to notice events that are almost never allowed to happen. And it treats silence not as emptiness, but as a sign that the messenger is difficult to hear. The neutrinos from that early era would not show us stars. They would not show us galaxies. They would not show us atoms in the familiar sense. They would carry information from a universe still too young, too hot, and too dense for ordinary light to become a clean witness. That is their importance. They belong to a deeper layer of memory, a memory before atoms were complete, a memory before transparent space, a memory from behind the wall that light could not yet cross. The universe had begun to leave records of itself long before it became visible. Some of those records are loud enough for telescopes. Others move through us every moment without asking to be noticed. The ghost particles escaped almost at the beginning. And ever since, they have carried one of the earliest silences in the cosmos. Before the first stars existed, the universe had already begun nuclear construction. That idea feels almost backwards. Stars are the furnaces we usually associate with the making of elements. They burn, compress, fuse, and later scatter new material into space. But long before any star could ignite, the early universe itself briefly became a nuclear furnace. It did not create the full richness of the periodic table. It did not make carbon, oxygen, silicon, or iron. It did something simpler, older, and more limited. It made the first light atomic nuclei. At this stage, protons and neutrons already existed. They were the durable pieces left after the earlier particle era. A single proton could serve as the nucleus of hydrogen, but anything beyond that required particles to bind together. To make helium, the young universe needed protons and neutrons to join in stable combinations. That was not easy. The universe was still filled with energetic photons. These photons were not gentle carriers of visible light in the familiar sense. They were powerful enough to strike newly formed nuclei and break them apart. So the early universe faced a bottleneck. The key bridge was deuterium. Deuterium is a heavy form of hydrogen made from one proton and one neutron. It was the first step toward building more complex nuclei, but it was fragile. For a time, whenever deuterium formed, the surrounding radiation could destroy it almost immediately. The bridge appeared, then collapsed. It appeared again, then collapsed again. The ingredients were present, but the path forward could not stay open. Pause inside that moment. Imagine a furnace so hot that every small structure melts before it can be used. A worker places the first beam across a gap, and the heat bends it out of shape before the next piece arrives. The bridge is not impossible. The timing is wrong. The early universe was like that. It contained the particles needed for nuclear construction, but the light around them was still too violent. Only as expansion continued did the temperature fall enough for deuterium to survive. When that happened, the bottleneck opened. Deuterium could remain intact long enough to take part in further reactions. From there, the universe could build helium nuclei. Helium was especially important because it was stable and favored by the conditions of the early cosmos. A helium nucleus could hold 2 protons and 2 neutrons in a compact and durable arrangement. Once the universe cooled to the right range, a significant amount of helium formed quickly. The process is known as Big Bang nucleosynthesis. It is one of the strongest links between nuclear physics and cosmology. The theory does not merely say that the early universe was hot. It predicts what kind of light nuclei should have been produced in that heat. Hydrogen should remain dominant. Helium should form in a major but smaller amount. Tiny traces of other light nuclei, including lithium, should also appear. That early recipe still matters today. When astronomers measure the abundance of hydrogen and helium in the cosmos, they are not only studying stars and gas clouds. They are reading a surviving chemical memory from the first minutes of cosmic history. The large amount of helium in the universe is especially important. It is difficult to explain as something made only inside later stars. There is simply too much of it, spread too widely, and connected too deeply to the early conditions predicted by cosmology. This does not mean every detail is effortless. Lithium has presented long-standing questions, because some observations do not match simple expectations as cleanly as hydrogen and helium do. But the broad picture remains one of the great successes of the hot early universe model. The young cosmos made mostly hydrogen and helium, with small traces of other light elements. Then the process stopped. It stopped because the universe expanded and cooled too much for nuclear reactions to continue efficiently. It also stopped because the early conditions did not provide an easy path to heavier elements. There were gaps in the possible chain. Stable stepping stones were missing. The universe could not simply climb from helium to carbon and onward through the periodic table. That later work would require stars. It would require gravity to gather gas into dense objects. It would require pressure and heat inside stellar cores. It would require time, collapse, fusion, and in many cases, violent stellar deaths. So the first million years did not contain the full chemistry of planets or life. It contained the fuel from which stars could eventually form. Hydrogen became the great reservoir. Helium became the ancient companion. Lithium and other light traces remained as small signatures of the earliest nuclear reactions. There is something quiet about this stage, despite the heat that created it. The universe was not yet shining with stars. It was not yet arranged into galaxies. It had no rocky worlds, no oceans, no dust clouds enriched by stellar generations. But it had changed in a permanent way. It was no longer only particles waiting to become matter. It now carried nuclei. It carried the first elemental pattern. And that pattern set limits on everything that followed. When the first stars eventually formed, they did not begin with an arbitrary mixture. They began mostly with hydrogen and helium. Their lives, their burning, their brightness, and their eventual deaths were shaped by that inheritance. The first elements were therefore not a decorative detail in the cosmic story. They were the first raw supply. They were the material condition that made stellar history possible. The universe now had fuel, but it still had no stars. Hydrogen and helium waited in darkness, spread through expanding space, until gravity could begin the next long act. For hundreds of thousands of years, the universe was full of light, but impossible to see through. That sounds like a contradiction. Light was everywhere. Photons moved constantly through the hot young cosmos, but they could not travel freely. They were trapped in a crowded plasma of charged particles, scattered again and again before they could cross any meaningful distance. This was not darkness in the ordinary sense. It was closer to standing inside a dense, glowing fog where brightness fills the air, but no clear view can form. Every direction contains light. Every path is interrupted. The universe shines, but it cannot yet reveal itself. The reason was electrical charge. At this stage, atomic nuclei existed, but electrons had not yet settled into stable neutral atoms. Free electrons moved through space with protons, helium nuclei, and radiation. Photons interacted easily with those free charged particles. Whenever light tried to move, it was redirected. A photon might begin a journey, only to be scattered almost immediately. Then it would scatter again, and again, and again. The universe was not transparent because light had no clean road to follow. Opacity in this case did not mean that light was absent. It meant that light was trapped in conversation with matter. It could not leave the crowd. Then the expansion of space changed the conditions. The universe cooled. The energy of the photons dropped. And eventually, electrons could join with nuclei without being torn away again, almost at once. This transition is called recombination. The name can be slightly misleading because it sounds as if atoms had existed before and were simply coming back together. In reality, this was the first time the universe could form neutral atoms in a lasting way. Protons could hold electrons and become hydrogen atoms. Helium nuclei could hold their electrons as well. The charged plasma became a neutral gas, and that change opened space. It did not happen because someone turned on a light. The light was already there. It happened because light was finally released from constant scattering. A photon that once would have been interrupted almost immediately could now travel across the universe. For the first time, the cosmos became transparent. Pause at that threshold. For hundreds of thousands of years, light had moved like a person trying to cross a packed room where every shoulder turns them aside. Then the room begins to empty. The collisions become rare. The path opens, and something that had been trapped in short, broken steps can suddenly continue onward. Those released photons did not vanish. They have been traveling ever since. As space expanded, their wavelengths stretched. Light that was once far hotter and more energetic cooled with the growing universe. Today, that ancient radiation reaches us not as visible light, but as microwaves. It is called the cosmic microwave background. This background is not coming from one object. It is not the glow of a star, a galaxy, or an explosion in a particular direction. It surrounds us from all directions. It is the faded afterglow of the time when the universe first became transparent. That makes it one of the most important pieces of evidence in all of cosmology. It does not show the literal first instant. It does not take us all the way back to the Planck era. It does not reveal the moment when space and time first became describable. But it gives us a real image of the universe when it was still young, hot, dense, and newly open to light. The discovery of this radiation changed cosmology because it matched a prediction. A hot, dense, early universe should leave behind a cooled remnant glow. When that glow was found, it gave the Big Bang model a powerful observational foundation. The signal was not a decorative detail. It was a fossil of transparency. It was a surviving surface from the young cosmos. But the cosmic microwave background is not perfectly smooth. That is just as important as its existence. It contains tiny temperature variations. Some regions are slightly warmer. Others are slightly cooler. The differences are extremely small, but they matter because they show that the early universe was not perfectly uniform. The universe had texture. It had tiny density differences left from earlier processes, stretched and preserved across cosmic time. Those variations are among the first visible signs of the structure that will later become galaxies and galaxy clusters. If the background had been perfectly smooth, gravity would have had nothing to amplify. There would be no preferred regions where matter could gather. No first clumps. No future cosmic web. The small irregularities are therefore not flaws in the picture. They are the picture's deepest value. They show where later structure could begin. Another imprint from this early plasma is known as baryon acoustic oscillations. The term sounds technical, but the idea can be approached through sound. In the hot plasma before recombination, gravity pulled matter inward, while radiation pressure pushed outward. This produced waves moving through the early universe, something like sound waves traveling through a dense medium. They were not sound and air. There was no atmosphere, no ear, no ordinary vibration, like a note from an instrument. But there were pressure waves in the mixture of matter and radiation. When neutral atoms formed and photons were released, those waves left a frozen pattern in the distribution of matter. That pattern did not disappear. It became part of the large-scale structure of the cosmos. Even today, astronomers can use these ancient ripples as a measuring tool for cosmic distances and expansion. This is one of the remarkable turns in the story. The early universe was once opaque, hot, and nearly featureless to the eye. Yet hidden inside it were patterns, temperature differences, density variations, pressure waves, the first usable map of structure. Recombination made those patterns visible in light. It transformed the universe from a glowing prison into an open record. After that moment, photons could travel across deep time. They crossed expanding space while galaxies had not yet formed. They moved through ages before the first stars. They continued while gravity slowly worked on the small differences they left behind. And now, after billions of years of stretching, they arrive as a faint microwave glow from every direction. This is why the cosmic microwave background is more than ancient radiation. It is a map, a quiet, cooled, all-sky imprint of the universe, at the moment it first became transparent. It tells us that the young cosmos was hot. It tells us that it was dense. It tells us that it was nearly smooth, but not perfectly smooth. And in that almost invisible unevenness, the future was already marked. The universe finally became visible, but what it revealed was not an ending. It was the first readable image of everything still waiting to grow. When the universe became transparent, it did not immediately become beautiful. There was no star-filled sky, no spiral galaxies, no glowing nebulae, no planets turning quietly around distant suns. Light could finally travel, but there was almost nothing yet that could shine in the way we recognize. The cosmos had opened its eyes into darkness. This period is often called the Dark Ages. The name can make it sound empty, as if nothing important was happening. But that is misleading. The Dark Ages were not a pause in cosmic history. They were a time when gravity began to work on the tiny differences left behind from earlier epochs. The universe was mostly hydrogen and helium, spread through expanding space. It was cold compared with its first moments, but not yet cold in any ordinary human sense. Matter did not instantly collapse into stars. It needed guidance. It needed time. It needed regions where density was already slightly higher than average. Those small advantages became the first places where gravity could begin to gather material. Here, the visible story depends on something invisible. Dark matter does not shine. It does not emit ordinary light. It does not absorb light in the familiar way. It does not reveal itself as glowing gas, dust, or stars. Yet its gravity appears to affect the motion and structure of the universe on enormous scales. This is why dark matter is not simply an invented name for ignorance. It is a name given to a pattern of gravitational evidence. Galaxies rotate in ways that suggest more mass is present than the visible stars and gas can explain. Galaxy clusters behave as though they contain far more matter than telescopes can directly see. In the 20th century, Fritz Zwicky studied the motion of galaxies in clusters and argued that unseen mass was needed to explain what he observed. Later, Vera Rubin's work on galaxy rotation gave another powerful line of evidence. Stars far from the centers of galaxies were moving in ways that did not match the expected pull from visible matter alone. The outer regions should have behaved differently if only the observed stars and gas were responsible. Instead, the motions pointed toward a larger hidden mass distribution. That hidden distribution became one of the great unsolved realities of modern cosmology. Dark matter is strongly supported by its gravitational effects, but its particle identity remains unknown. It may be made of particles not yet detected directly. It may require physics beyond the familiar matter described by the Standard Model. What matters here is not that we know exactly what dark matter is. What matters is that the early universe appears to have used its gravity before the first stars formed. Dark matter could gather into halos and filaments. These were not visible structures, but gravitational shapes. They acted like invisible valleys in the landscape of space. Ordinary hydrogen and helium could fall into those valleys. Where the wells were deeper, gas could collect more efficiently. Where gas collected, it could slowly become dense enough to cool, compress, and eventually ignite. This is how darkness can prepare light. The first stars did not appear from a perfectly smooth universe. They emerged because the cosmos had texture, because gravity had uneven places to amplify, and because unseen mass helped define where ordinary matter would gather. Pause on a modern field of galaxies. Each point of light may seem like a separate island. Each galaxy may look like its own bright city in the dark. But beneath that visible arrangement is a deeper pattern. Long before those stars existed, gravity had already marked the routes. Dark matter had helped draw the riverbeds before ordinary matter flowed into them. The galaxies are not only collections of stars. They are fossils of invisible structure. That idea changes the feeling of the first million years. The universe did not spend that time merely waiting. It was setting conditions. It was cooling, separating, forming particles, preserving tiny irregularities, releasing ancient radiation, and allowing gravity to begin its slow work. By the end of the first million years, there were still no familiar galaxies. The first stars were still ahead. The chemical richness needed for rocky planets and life was still far in the future. But the path towards structure had become possible. The raw material existed. The first light had been released. The small density differences had been recorded, and invisible gravity wells were beginning to shape where matter would later collect. Modern cosmology adds one more unsettling perspective. Dark matter is not the only unseen component in the cosmic story. Dark energy is the name given to whatever is driving the accelerated expansion of the universe. That acceleration was inferred from observations of distant supernovae and has been supported by other measurements. Dark energy is not part of the first million years in the same direct way as dark matter's role in structure formation. It belongs to a later understanding of the universe's expansion. But it reminds us that the cosmos is still not fully transparent to the mind. The matter that forms stars, planets, and bodies is only a small fraction of the total cosmic inventory. Most of the universe is described through things we know mainly by their effects. Gravity reveals one hidden component. Expansion reveals another. Light shows us much, but not everything. That is where the story settles. The visible universe is a late consequence of invisible conditions. The first million years did not give us stars, but it gave stars a future. It did not give us planets, but it prepared the matter from which planets would one day be made. It did not give us the night sky, but it created the structure that would later fill it. The room had gained many keys. Forces had separated. Matter had survived. Nuclei had formed. Light had escaped. Gravity had found uneven ground. But not every door opened. Some remain closed even now. And across the modern universe, every galaxy still carries the imprint of that early darkness, shaped by things that could not be seen, but could not be ignored.